talking to you about a case study that we are currently implementing. So we are a company that faces several challenges. Most of them are in the networking layer 2 field. So a lot of our equipment is networking based on layer 2 equipment. In this case, we are working with different companies on a project in Israel. And this is a new ropeway project. So this will be built in Haifa, which is in the north of Israel. And it's rather mountainous there. So the problem there is public transport. Buses are limited in capacity. Subways in a mountainous area is a real pain to build. So the easier solution was to use a kind of cable car. In that case, it's called ropeway. It's more or less a cable car system that's permanently running. It will consist of 6 stations, and in total there are 36 pylons. So these 36 pylons host the cable, and the stations are to get on, get off, and also to change the cables, so that not all cable cars are on one single cable. It's a little bit splitted. The pictures I put in are not from this project because they are still building the pylons. So it's not real life. But the larger one, with the red cable car, this is in South America, in La Paz. It's already up and running. And it's very successful there. They have a whole ropeway network now because it's way cheaper to implement than a regular subway or a tram system. And especially in geographically challenging areas, this is a really nice solution and very, very cost effective. So the problem there is you need some access to security data there. And the most important thing for the cable car is the cable and the rollers on top of the pylons. So the ropeway system has a detection system that is able to detect if the cable is still running correctly on the rollers. The problem here is it's not 100% accurate. So sometimes the system would tell you the cable is off and stop the whole ropeway, but in fact it's not. So in addition, there are cameras mounted on each pylon that look at the cable rollers and check if the cable is really on there. So whenever the alarm goes off, the camera switches on, and the operator sees the picture of the pylon, of these cables, and can tell if it's actually a problem or it's just a false alarm. So to get that information back to the operator, we are implementing a network there. So the main function of the network is to supply the operator with that information. The secondary function is it's also used as a voice over IP network to communicate directly with the cabins. So if somebody presses an emergency button, then they can talk to the operator via voice over IP directly. And the third function is to provide wireless internet access on the cable car. So we have 3 different things that we had to implement there. As you can probably guess, the main design goal for the whole thing was to make it as reliable as possible. So we were looking into different possible solutions. This was, our first thinking was we use a double ring system. So we place switches in the stations, A to F, these are the stations. We connect them with a ring for redundancy, and we make a secondary ring along the pylons, all with fiber optic cables. So The drawback on this solution is an error in 2 stations at once. So if 2 stations fail, like A and F, then there is a lot of communication capability lost. Actually, in this design, there would be no communication to all the pylons. This is not really acceptable for such a system. So we came up with a different solution. And the different solution was to use a mixture of what we call chain and ring technology. So CTS has developed redundancy technology. It's called fast ring. It's very, very easy. So basically, to configure it, it's really a matter of seconds on a web interface to configure a fast ring interface. And the second thing is it has 2 options. One is ring and one is chain. A chain is basically the same thing, just open. So it has 2 ends. The interesting thing here is that we can do this later in the process. So when we first started the whole project, it was not sure what technology they would like to use, how it should be implemented, which IPs they would use, what the cables would be. So we needed to keep it totally flexible. And this solution covers that. So what we did is we draw them a little plan like this, a little bit more detailed, but basically all the real information is there. So the little triangles indicate ports that are just shut off. So before you install it, you just shut off these ports. After that, you just install all the equipment. So we pre-configured management IPs, but that's all. So you can just plug it in and set it up. There is no need to go to any pylon anymore for reconfiguring it. We can all do it remotely because we made sure by switching off these ports that we don't have a loop in the network. So after we have the basic installation, we can then decide what we actually want to do, switch on the redundant technologies like the chain or the ring, and switch on the ports again. After that, we're fully redundant without really going to on-site, which was one of our goals because it's always a pain, especially if you have systems like this. And 36 pylons, each pylon about 500 meters apart. It's quite a walk if you have just to walk there or you take a taxi there. It takes forever. And so we were able to just send them the equipment pre-configured, and they just put it there, plug the plugs in, ready. Everything else we can do remote, which is nice and very efficient. So this was the final solution there. What we used for this solution was the IPS 3110. It's an industrial type of switch. It is a plain layer 2 switch, no layer 3 capability, just layer 2 capabilities. And for this project, we needed a wideband DC power supply. So it covers everything from 24 volts to 56 volts DC. Everything is fine for that switch. So you just use whatever you have on DC powered there, and it will work. The only thing that you have to be careful is that the DC power has enough wattage to supply PoE. So if you would put a 24 volt, 1 amp power supply there, the switch would boot up, no problem, but PoE wouldn't be possible. The stations will be equipped with the EPS 3128. It's a 24-port PoE switch with 4 combo ports for fiber optic uplink, and there we're going to connect things like telephones to it directly. And we also use that on single mode fiber, so we supplied fiber SFPs to them. And there's nothing really complicated with SFPs. The The only thing in that case is they needed a wider temperature range because it gets pretty hot in Haifa. And especially in those small cabinets that you put on the pylons, they are in the sun. So in summer, they get more than 70 degrees. So you need equipment that can withstand at least 70 degrees. So we used equipment that is perfectly fine with 75. And actually, if it's 80, it won't really hurt it. It's certified to 75. So this is the 3110. Here there's 8 RJ45 ports, 2 combo ports for SFPs and RJ45, dual DC input, so you can also have redundancy there. It's managed. It has a power budget of 120 volts at 24 volt input power or 240 watts at 56 volts. And it uses the fast ring version too, which I think is a good thing because it's so easy to configure. The customer decided for these switches because the fast ring is so easy to configure and easy to replace. So usually, if you've been working with ERPS rings, for example, you know that ERPS can be a real pain to configure. There is a lot of things you have to take into consideration, and most of the time in an ERPS environment, you have to replace a switch with exactly the same configuration on exactly the same ports. So just mismatching the cables would kill the ring immediately. Fast ring is not really prone to that problem. If you mismatch the 2 fiber cables, doesn't matter, still works. So it's way more resilient in that way that you're not able to easily break it just by making one single mistake. With ERPS, this is always the problem, especially if you have untrained personnel that is going on site and is changing things. So this makes it way easier, and it also works if it's not configured. So even our design is built in a way that even if you put a non-configured switch in, it would still work. It would not be redundant, but it would be enough to make it work, to supply the functions that the customer needs, and to give you the ability to configure it correctly remotely. So another nice feature is surge protection. It's K21 surge protection, which is also interesting in this installation because you very likely have lightning strikes on the pylons. And a single lightning strike should not really destroy the switch. If it's a direct hit at the switch, no way that you can prevent it from bursting into flames. This is too much energy. But if it's a near hit or an indirect hit where it's not directly in the path, which is most of the time the case, then it can actually withstand it. It can work up to 6 kilovolts input voltage, and it would still work. So the camera, for example, on the rollers would be completely damaged by this, but the switch itself would work and still would provide redundancy for the network. So for the EPS 3128, it's a regular 24-port PoE switch with copper ports plus 4 combo ports. So you have the choice of RJ45 and SFPs. But there's no PoE power to those ports. The maximum power would be 480 watts. If you really need it, it's pretty powerful, but my experience is that 240 watts is in a regular environment enough because you don't want too much power to be drawn from one single switch. This could also have redundant reasons, and most devices don't require more than 30 watts. They're just special devices that really require more, like PTC cameras with heating that can go up to some like 50 watts, but that's not the regular case. It's also managed It also has the fast ring features that we usually just implement in the industrial type. This is not an industrial type of switch. So it's a regular switch. It's also suitable for the office or enterprise environment. And it's not extended temperature because the stations, they're climate controlled. So there's no need to have an industrial larger switch. Basically, that's all I have to say. So if you really want to know some details, I'm very happy to talk about that. But basically, I'm finished. Just one thing. In the whole testing process of the fast ring, the customer asked how many devices could be in a fast ring and it still works with a reasonable time to switch over. So we tested that. We tested 200 devices, and the recovery time was less than 50 milliseconds. So it should suit a lot of applications with this performance.